Events. Thanks, Joe.
All right, great. All right, good afternoon, everybody. And yeah, I'm going to be talking about my paper, VESTA, Power Modeling with Language Runtime Events. So first, a bit of an introduction to why power modeling in the first place. Well, with power modeling, we're interested in, energy efficiency, understanding how much power certain applications are consuming, right? So when it comes to that, right, everybody here, they have mobile devices of some sort. They've got batteries on them, and you'd like those batteries not to instantly, dissipate, right? So if we write programs that take up less power, be able to use our devices longer, that also sort of corresponds to, say, data servers, right, which are running millions or, thousands and thousands of different programs at a given moment. And if we have those programs consume less energy, then there'd be less operational cost, associated with that power consumption. That then sort of goes with, more power means more heat, and therefore the more need to cool those data servers, so less power, less heat, less cooling. And also if we're concerned with energy efficiency, right, or if we're concerned with wanting to continue to use our technology stacks or whatever for a longer period of time, right, if we think about the future, we want to make sure that we can continue doing what we're doing for as long as possible, right? And if we want to be doing that, we want to reduce the amount of power that all of our devices or applications are consuming, right? So if we're then interested in energy efficiency, we're very much then going to be interested in power modeling, kind of the pillar of energy efficiency. And normally, if you're building power models, state-of-the-art gold standard is using an HPC-based power model. So what are HPCs? They're hardware performance counters, so registers on a CPU that are going to tick up, keep an accounting of any time, say, a TLB miss occurs, a cache miss occurs, a floating point operation, something to that effect, right? And normally you'd build a power model based on that. So you'd have some kind of linear model that then maps these different counters up to power consumption, right? But there's a few limitations to doing so. One of which is if you're trying to model the power for an application, right? You're violating the principle of least privilege there. You want an application power model, right? You want to know how much that application is running. You're going here, you're stepping outside of the boundaries of the application and going down into the hardware, right? And also these HPCs, they're going to get ticked up regardless of just your process, but other processes running on a given machine, okay? That also gives kind of a difficulty when wanting to explain logically what's going on with these models, right? What does it really mean if you have, say, millions of cache hits causing power, a larger power drain, when, again, multiple processes can be running at the same time, right? It's not specific to your application. So then the question is, can we do better than that, or at least, for those particular problem points? Can we build some kind of power model that uses application-specific language runtime events, okay? And of course, for VESTA, the answer to that is yes, we can do that. So VESTA provides a novel methodology that uses JVM events to build power models. So here, by using JVM events instead of HPCs, what we're doing is we're capable of satisfying the principle of least privilege because we're just inside of the application domain, right? We're not jumping down into hardware specifically. And ideally, right, all those different events that we're tracking are going to tell us something about the application itself, right? So our model is going to tell us, or at least give some kind of indication to a developer perhaps of saying, oh, this is why I consumed more power in this instance, okay? In terms of the tool itself, VESTA is very lightweight. It's capable of predicting energy with a mean average percent error of our 37 different benchmarks that we checked of only 1.53% error. And in the paper, we provide a study on event importance and model explainability with these JVM events. Okay. So in terms of the design of VESTA, it's pretty simple and hopefully decently intuitive here. Basically what we're doing is we have these JVM events, we have some energy, right? We have an application that we're looking at and monitoring. From that, we then create a trace using that event and energy data, right? So bucketing together all this information, building a model out of it, and then ideally having some nice accurate predictions. Now in terms of how we get that energy data, what we use, since we're JVM focused, we use a tool called JRAPL. It's kind of a wrapper around Intel RAPL, which is going to interact with that C interface to get power readings and energy readings. From that, how do we get our JVM events, or what exactly are the JVM events we're using? Well, we use these things called USDT probes, so that stands for user statically defined trace points. kind of locations inside of the hotspot OpenJDK that we were using for our testing that's going to give us indications of when certain events occur. Okay? And there's quite a lot of these events that exist in the JVM. So here is kind of a snapshot of the events that are available. So these are the 24 different probes that we monitor. And you can see that they're very diverse. They tell you a lot about the application's runtime. So method probes, JIT probes, memory management, exception handling, concurrency, a lot about how the application is running, right? So things about garbage collection, new objects being made, et cetera. However, in reality, the probes don't really look this nice from sort of the outset. Most of the probes that exist in the hotspot JVM, 94% are what we call split phase. So really, they look more like what's shown in this table, where we have events that have entry and return behavior. So we see get long field entry, get long field return. Whenever we step into getting a long field, that entry fires. When it finishes, it returns. Okay, so that's the idea, or those are the probes that are initially exposed. So the difficulty then, and what's different between HPCs is the HPCs, right? The cache miss is it's a single event that ticks the counter up. It's not quite the same thing with our language runtime events because we have normally multi-threaded processes, right? The JVM is going to spawn a bunch of different threads, and then perhaps have a lot of these events occur at the same time. So what does that really mean to have, say, 5 get long field entries and no corresponding exit? Right? So it's kind of a difficulty here. The way we solve that is through this idea of tracking these split phase events and taking note of their state and their intensity. So there's a more formal description of how this is done in the paper, but hopefully this provides kind of an intuition for it. The idea is that we have our different timestamps with all of our different events being fired. And if we see, say, like what's shown here, an entry, we're going to tick up that depth. We're going to keep doing that. So in the next timestamp, we see another entry. We're now at depth 2. In the third timestamp, we see an entry and an exit. We're going to tick up the depth, but keep note of the fact that we saw an exit, so in the next timestamp, we decrease the depth, saying, the idea here being that we're keeping track of all these different events occurring and trying to understand the state of the runtime system as it's executing, okay? So that's really what we're matching to power. So another unique challenge associated with VESTA here is the idea that we're not, unlike HPCs, which traditionally they use linear regression techniques, right? So a linear regression model, which fits quite nicely with the intuition of how these HPCs can be mapped to energy. Insofar as you have a cache, different levels of caches, TLB, an ALU, right? All these different components that when added together gives you the total power consumption of that device, right? It's not quite the same. We didn't find that to be the case with our runtime events. These JVM events, they didn't have that kind of nice additive behavior associated with them. They're very nonlinear in the way that they were structured. Okay? So at the end of the day, we had to choose a then nonlinear model in the form of a decision tree. So for VESTA, we used XGBoost, which is a gradient boosted decision tree, and it worked quite well for our data set. We also explored using linear models and neural networks, which you can find in the paper on how that went, not particularly well, as opposed to the decision tree. Okay, so for evaluation, some experimental stuff, we used 37 state-of-the-art JVM benchmarks, so 14 from DeCapo, 23 from Renaissance. More on the machine information and all that in the paper, and the default configuration for the JDK we used was OpenJDK 19, but more on that in a little bit. So the whole point is we're building a power model, right? So the theoretical stuff is nice and interesting, but does it actually work? And the answer is yes. It works pretty well for us, very well in fact. Like what was mentioned before, we have a mean average percent error of all these 37 benchmarks of only 1.53%, meaning that for overall power prediction, VESTA does quite well. Okay? You also have the capability, so this is something that you could look at. All these graphs can be replicated for yourself on using the artifact that we have. You can see you could look at a per trace that here we have a black line indicating ground truth, blue line indicating the blue dash line indicating the prediction for VESTA of those different timestamps, and that the model does a pretty good job of managing or understanding the trend of power consumption for here the DOTI benchmark, so with only an error of 0.74%. Okay. Now, what's really interesting about VESTA is the idea of explainability, right? Since now we're kind of at the application level, we can see how things about how the program was written is really going to influence power consumption. So what's shown here is a graph detailing feature importance. So what we see is a ranking from the least important to our most important features using SHAT values. So if you don't know what that is, it's a pretty popular metric for machine learning that indicates with a high average or a high absolute value that that particular feature had, for our purposes, quite an impact on the power state, on dictating to the model when the state is fluctuating in one way or the other. And what we find is that kind of intuition about certain aspects of a runtime system does, in fact, influence power consumption, like concurrency with thread park, memory-related tasks like GC, creating new objects and setting objects. Right? So we find that those being the most important in making decisions in energy fluctuation for VESTA. We can also go and look at exactly how the different splits occur in the decision tree. So here it's a little bit cropped. In reality, you could look at a much more detailed decision tree with all the different branches. The orange highlight is showing exactly where the splits are occurring. And we can see that for this kind of arbitrary trace, we're going from one split to another to eventually get our predicted power for that interval of 56 watts. So the idea is that, if a developer is looking through this, they could have some understanding of how their application is moving from one power state to another. So I mentioned before, I made the claim that VESTA is pretty lightweight. Here we see some overhead stats. Energy, only about 2% overhead. Reference cycles, 3%, and wall clock time, a little bit less than that. So VESTA is a very lightweight tool, which does not impact too much the actual behavior of the applications we're taking a look at. So I mentioned before that we didn't just use the OpenJDK19, or at least we used that as kind of a default. We wanted to make sure that this wasn't just a fluke on our given machine, right? So we used a bunch of different configurations and combinations of things to see does VESTA work just as well. So we tried different GCs, so the default being G1 GC for JDK19. We tried the serial, parallel, ZGC, all these different JIT compilation or different JIT configurations, a different JDK, so going from 19 to 11, that worked just fine, and also trying out VESTA on different machines, right? So still Intel CPU since we're using RAPL, but a different CPU, different Linux kernel, different setup, all that, and it worked just well. More details on that in the paper itself. Okay. So some additional results not shown here, but in the paper, we also went through and recreated sort of the classic linear regression-based HPCs. We also showed exactly what would happen if we used language runtime events for linear models and neural networks. Again, more details on that in the paper, but the idea, since this is kind of the linear regressions, that nonlinear behavior doesn't work out so well, and the neural networks seem to be a bit overkill, at least for what we tried. So in conclusion, VESTA provides a novel approach that uses JVM events for power modeling. It explains power consumption at the application level, right? And it manages to satisfy the principle of least privilege, the idea that we're not going down and looking at hardware performance counters outside of the scope of the application itself. Right? We're just looking at information that can be gleaned from the runtime and from the application. It's low overhead and highly precise, exactly what you want from a power model. Okay. So thank you for listening, and does anyone have any questions about VESTA?
If you could remember to state your name and affiliation. Thanks.
Miliana Sabatovich, University of Maryland. I was curious on your graph showing the mean average percent error.
Mm-hmm.
There's a couple benchmarks that spike a bit higher, right? Do you have any insight as to
Yeah, so we talk about that a bit in the paper. Two of them, so our decision, and we also discussed why we chose this in the paper too, but we had a 1 second bucket for our timestamp data. And we also, some of the benchmarks in the benchmark suites run for like 1/3 of a second. So we weren't really grasping quite a lot about the runtime itself. Since we all, we chose the same number of iterations for all benchmarks, they kind of had less data associated with them. So then, for a model, you're going to have less information to train on. So that was for a couple of them. One other, it's possible we have a screening process for choosing the lowest overhead nodes. Again, more on that in the paper. And it's possible that a node or that an event that was very useful for one of the mispredicted lines of Scaladoku, perhaps that we lost information from dropping one of those events. So that's some kind of indication as to why those didn't perform as well.
Thank you.
Great, thank you for the question.
Matthias Böhm, TU Berlin. So super interesting talk, and you showed
you.
those errors for JIT and GC, kind of how much you mispredict, and you showed the sharp values. But just out of curiosity, what is the absolute value of power consumption of different JIT versions and different GCs? So could you quantify how much % of total power consumption do we actually spend in those meta services of the JVM?
I was saying, if I understand the question correctly, the idea of what's the difference between jumping from one model with a given JIT configuration?
No, in general, just out of curiosity,
Yeah.
for JDK 19,
Yeah.
so how much % of total power consumption do we spend on GC? So not what the error is, but what is the actual absolute value? So just out of curiosity.
So we don't track exactly, we don't have any information on that specifically, in the paper, any experiments that we tried. Perhaps something that could be done. I don't have any information on that specifically.
Okay.
Thank you for the question.
Hi, I'm Kunal Sareen from the Australian National University, and thank you for the interesting talk. I have a couple of questions.
Sure.
So I wonder why you picked USDT probes instead of JVM-TI events. Maybe this is a slightly technical question. And the other one was, you've done all this great work, but I wonder what insights do you have on what sort of optimizations we can do to actually improve power efficiency of applications and benchmark and programs.
Okay. So I'm not familiar with what was the other?
Oh, it's JVM-TI,
I'm
tooling
not familiar
interface.
with those, so I guess I can't say. I can say for the USDTs, the reason we chose those was a decision made a very long time ago, is the idea that we do have an ability to look pretty low level into what's going on in the runtime. That's why and it's not too hard to get information from it.
Yeah.
In terms of what could be done to manage, have lower power being expended from applications, I think that would have to be further work. I don't know exactly what, say, the developer would have to do in a given instance to tweak one thing or another, some level of measurement, and hopefully the VESTA here provides some kind of insight into, at least we know concurrency, GC, all that stuff, it really does have an effect on energy, and it's very important when it comes to at least this modeling.
Of course. Thank you.
Thank you.
Hi, I'm Luis Pena from University of Illinois, Chicago. Great talk. There was one source of power consumption that I was surprised not to see mentioned, which were system calls. Did you track those at all?
There's prior work, so nothing we did, but there is prior work of using system calls to build power models. The exact name of the paper escapes me right now. But there is work that's been done for that. And we didn't track system calls because we wanted to keep everything inside of just JVM runtime, right? So we didn't want to sort of step outside of operating system or things like that. Yeah. So that's why we didn't do it. But it has been thought of before, and it is, it's an interesting idea as well.
And a follow-up of that, probably you didn't do it because you didn't have a probe that when a system call happens would be done.
Yeah,
What other probes do you think you'd like to have that you don't have?
It's an interesting question because there's quite a lot of them. And there are interesting ones that we kind of have to drop because tremendous amount of overhead because they get called all the time, things like method invocations and stuff like that. But yeah, I don't know exactly. I never really thought about what are we missing from the whole space, because we do find quite a lot of disparate and descriptive probes. But yeah, I don't know exactly what. It's an interesting question of what's missing. I don't know.
Okay. Thank you.
Thank you.
We're running nicely ahead of schedule here, so I'm going to indulge in a question if you don't mind. Yeah, I guess one thing that came to mind for me, and I think maybe Kunal touched on it in his question, was how do you envisage developers using this? One application I can imagine is, my thing seems to be a bit power hungry. Why?
Yeah.
and the developer asking that question and trying to use this to look at that?
Yeah.
Is that what you had in mind or not?
I think as the tool exists right now, there's probably limitations when it comes to what a direct developer can really influence. Really, the crucial idea of VESTA is that we can build these power models from language runtime events, right? And maybe in the future have them, have it be more refined and figure out exactly what's doing what, instead of just knowing now that we can do it, I think is what's most important here.
Right. Thank you.
Thank you.
Let's thank Joe.